Metastability occurs when the input changes within the aperture time, so when the dynamic discipline is violated. So when does metastability occur? It occurs when we have asynchronous inputs, for example, user inputs. We don't have a clock that determines when we can press our keyboard, for example. And it would be ridiculous anyway because we can't react within nanoseconds. So here's, someone pressing a button, and that input could be going into a flip-flop. And well, it could be fine, right? Here's the aperture time of the flip-flop. And it could change before, right? This D input could change from 0 to 1 before the clock edge, after the clock edge, no problem, case 2. But case 3 is a problem. Do you happen to press that button right within that setup and hold time? So now, instead of getting, right, if we draw our internal picture of our flip-flop, L1 and L2, when clock is 0, L1 is sampling into that internal node N1, and maybe it just got up to, instead of getting up from 0 to 1, it only had time to get up to half instead. And so now we have a problem because what gets sampled when the clock goes from low to high now is half. Instead of a 1 or a 0, we get a half or 3/4 or something that's not 1 or 0. And again, remember, those are voltages. And so metastability actually occurs whenever we have a bistable device. So with the flip-flop, we have two stable states, the one where Q is 1, Q is 0, but we also have a metastable state between them. And if the flip-flop lands in a metastable state, it could stay there for an undetermined amount of time. It could be a very long time, could be a short time, but if it stays there for a long time, now we have, instead of 1 volt or 0 volt on the output of our flip-flop, we have half a volt or something that's not 1 or 0. And the problem is it's driving combinational logic. And some of that combinational logic may interpret that as a 1, and some may interpret it as a 0. And so now it's not going to function at all like we expected, and maybe this is controlling an X-ray machine. And now the dosage isn't the right amount because our circuit malfunctioned. Or maybe it's controlling a kid's toy, and you turn it on and off again, and it works again. So, but if, in the medical application or other applications, driving, etc., this is a critical problem. So remember that a flip-flop is built from an SR latch in its internal circuitry, which in turn is built from cross-coupled NOR gates. And so when it's in the memory state, the SR inputs are both 0, and we get 0 or something, turns out to be, Q. It's just Q inverted as Q bar. And so these NOR gates that have the 0 connection, basically get rid of those, right? It's basically 2 inverters that are cross-coupled. Right, so we get Q coming over here. Q or 0 is just Q inverted as Q bar. Q coming down here is just the inversion of Q. Q bar. And if we redraw these, right, we've redrawn these before, like this. So we have this this output Q, or this output Q is feeding back to the input of the other inverter, and this output is feeding back to the input of the top inverter. And then we can redraw it. So we've redrawn it this way, and we can redraw it again. Well, 2 inverters back to back is just a buffer. And so, we have the output here, we have the input here, and we can draw what happens. So, well, just any buffer has some DC transfer characteristic. We have the input on the x-axis, the output on the y-axis. This is the voltage. And a buffer, let's just draw this transfer characteristic without feedback. So if it gets a low input, we expect a low output. If it's a high input, we expect a high output. And there's some transfer between those two. And so what happens when we have feedback? So this is essentially what we have when we're in the memory mode. Has some value. If it has a 1, for example, well, this is a 1 output. It's going to feed back to the input. It's going to come around and become the input. And input high, yep, it's going to still output high. It just kind of stays there, right? No problem. But if you have a 0, what happens there? Well, let's see, 0, that comes around here and becomes the input. Great, we get an output of 0 and it stays there, right? So what happens when it's neither of those? What if it's somewhere in between? So what if it's like, I don't know, about a quarter or a third? So instead of having a 1 or 0, instead we have now like a third. And that's our output. So here's our output, which is, let's say, a third. It comes out back and becomes the input. So now we go to our input, which is about here, a third, and it drives it to some other place. Looks like maybe a fourth or a fifth. And so that output gets driven here. So instead of being a third, now it's driven down to a fifth. And then it comes back around. That fifth comes to input, which is maybe here. And that drives it even further down to, I don't know, 20th or something. And so it does have feedback, so it actually drives it down to the rail to 0. And same thing would happen for driving it up to the rail. If it were not 1 or 0, but it were close, it would drive it somewhere close to the rails. So now let's see what happens when it's something like this, and we have this feedback on here. What happens if it's somewhere like where we have some line with a slope of 0, where it's exactly 0, exactly equal? And so let's say it's that, maybe it's that this is 1 and this is 0. Maybe it's at like a 0.4 point or something, or even doesn't have to be a half, but let's say it's 0.6 or something. And so that output is 0.6, that becomes the input, 0.6, output still 0.6. So now it's here. It's at this metastable point where it's like, oh, yep, we're good, 0.6, yep. That gives me that same thing as the output. Okay, that becomes the input, great. So now we're stuck here at this metastable point, or something very close to it, I guess it could also get stuck there. And so this is our metastable point. So it becomes a metastable signal if it hasn't resolved to 1 or 0, and gets sent to the rest of the circuit, combinational logic. So this means that if the input changes at a random time, and specifically during that aperture time, there's a probability that the output Q is metastable. And that probability is stated like this. So the probability that the resolution time is greater than some time that you've waited is T0 over TC e to the minus T over tau. where T naught and tau are properties of the circuit, and T resolution is the time to resolve to a 1 or a 0. So the probability of that time is greater than the time you actually waited, E, in that equation, E to the minus T over tau, is given by that equation. And so intuitively, T naught over TC is the probability the input changes at bad time. So if you have some aperture time, so T naught is related to the aperture time. If you have some cycle time and you have the aperture time around that cycle time, well, the probability that you're going to write the cycle time, you could also say that cycle time would go from here to, that next aperture time starting around the clock edge. Well, that probability is basically TA over TC. A probability that you're going to press it, right in here versus, sometime outside of the aperture time is just the time, the ratio, TA over TC, which is, so TA is related to T naught. So that's the probability that you're pressing it at a bad time in the first place. And then this tau is that time constant, right? Basically how fast it can either get driven up to a rail, or if it's below that midpoint, being driven down to the ground rail, to the 0 rail. So if the flip-flop samples the metastable input, if you wait long enough, the output will have resolved to a 1 or 0 just because of that feedback with high probability. Never 100%, but with high probability.